I'm Norman Wildberger. This is a course in hyperbolic geometry, a new way of thinking about the subject, a better way and more beautiful way. And today we move to the second part of the subject, where we're going to look at metrical issues, metrical notions, measuring, computing things, making calculations. Now, I've just returned from 3 months traveling. I'm on sabbatical from the University of New South Wales currently, so I have lots of time to think about things. In particular, I've been thinking about hyperbolic geometry quite a lot, and I've had a very productive and pleasant time traveling in Canada and the United States, visiting the Czech Republic and South Africa and Perth as well. All great places. So I have lots of enthusiasm now, and I have a few months ahead of me to do lots of YouTube videos, so I hope I'll be able to keep you supplied with lots of videos in the next few months. So today we're going to talk about quadrants and spread, which we've already discussed, but we're going to introduce them now in a more formal, more precise way. And this is going to be the start of this second part of this course. We're going to talk about metrical notions, measurement. And a big difference between this and other courses is we're going to be able to do everything over the rational numbers because we're doing everything completely algebraically. Everything is much more precise, much more careful, much fits together much more clearly and compactly and pleasantly than in traditional courses. There's no waffling here, or there at least shouldn't be if I do things right. So ordinary classical hyperbolic geometry, that's taught in hundreds of universities around the world these days, uses distance and angle as the fundamental measurements. Very unfortunate situation because, as you may know from studying rational trigonometry, distance and angle pretty well doom you to misunderstanding geometry. Rather, what we do in universal hyperbolic geometry is introduce the notions of quadrants and spread. So quadrants is a measurement between 2 points, and points for us will typically be small letters, A1, A2, and the quadrants between 2 points denoted Q, small q. Lines are denoted by capital letters like L1 and L2, and we're going to introduce the spread between 2 lines, which is also a number, and it's denoted with a capital S. So although these terms are the same as used in rational trigonometry in the ordinary Euclidean plane, they have quite a different definition, quite a different interpretation, quite a different meaning here in this hyperbolic setting. So probably, strictly speaking, I should put the adjective hyperbolic in front of these terms, but I won't do that here because we're always going to be in the hyperbolic setting more or less unless I say so. Alright, so these are hyperbolic analogs of the rational trigonometric quantities, which are denoted by capital Q and little s. Now it's possible for you to join this series with this lecture here. Because I'm sort of starting a new point, I'm kind of going back to the beginning in a way and going carefully in a sort of an introductory fashion for a little while. But let me remind you of some things that I've said before but are worth repeating. From my point of view, the big distinction in geometry is not between Euclidean geometry and non-Euclidean geometry, but rather between affine geometry and projective geometry. So what's usually called Euclidean geometry sort of fits on this side. What's usually called non-Euclidean geometry fits on this side. But it's really the affine versus the projective natures which is the critical, crucial distinction between these 2 sides of geometry. Over here, we not only have Euclidean geometry, but also relativistic geometry, as appearing in Minkowski, Einstein's approach to relativity. Here's where rational trigonometry takes place, as described in my book, Divine Proportions, Rational Trigonometry to Universal Geometry. Over here, well, we have the hyperbolic geometry, which is the main object in this course, but we have a related geometry called elliptic geometry, or sometimes pretty close to spherical geometry. And we're calling this universal hyperbolic geometry over here, and at least for the first part of this section, the paper Universal Hyperbolic Geometry 1, Trigonometry, which is on the archive, my paper, is perhaps the main reference in written form, aside from these videos. So I want to talk about the distinction between these two types of geometry and the different notation that we want to use to keep ourselves straight about the differences here. So in the Euclidean affine setting, we use capital letters for points and small letters for lines. We use capital Q to denote the quadrants between 2 points, which is some kind of measurement of how far apart they are. And we use little s for the spread between 2 lines, some kind of measurement for how far apart 2 lines are spread. In the projective setting, which includes our hyperbolic case that we're mostly interested in here, the notation is the reverse. So points are denoted by little letters, while lines are denoted by capitals. The quadrants between 2 points is denoted by the little q, generally by a little letter. The spread between 2 lines by capital S, generally a capital letter. So we can tell sort of from the notation whether we're in the projective setting or in the affine setting. For most of this course, we are going to be in this projective setting. But I'm going to start off today by comparing our approach to trigonometry in the affine and the projective setting. The comparison is particularly interesting and instructive. One feature that we have over here on the projective side that we don't have over here is duality, a very important distinction between the two. In hyperbolic geometry, points and lines are dual, as we've seen. That's a duality that goes back to Apollonius. And we're going to see that the fundamental measurements of quadrants and spread are also dual, a duality that reflects the duality between points and lines. This is a very interesting feature of the trigonometry over here, which is completely missing over here. Whether you work with distance and angle or quadrants and spread in the Euclidean setting, they're quite different kinds of objects and they behave very differently. But in the hyperbolic setting, quadrants and spread are completely dual. So I'm going to start by reviewing the fundamentals of rational trigonometry for you. This is not the trigonometry that we're going to be doing in this course, but it's the affine analog of it. And it's especially instructive to place your understanding of hyperbolic geometry sort of in opposition to what happens in the Euclidean setting. So let's review the basics of rational trigonometry in the Euclidean plane. And I remind you that the Wild Trig YouTube series discusses all of this and many applications in great depth. So in the plane, a point is by definition a pair of numbers x, y, which just represents a usual point in the xy plane. A line is determined by a proportion a to b to c of numbers in pointy brackets, with a particular requirement that the first 2 numbers cannot both be 0. One of them can be 0, but both of them cannot be 0. So AB cannot be equal to the point 0, 0. And we connect this with our usual equation of the line by this definition of incidence. We say that this point is incident with this line precisely when A times x plus B times y plus C equals 0. Now notice this plus C here. That's a little bit different from the convention that we've been using in lines in this course in hyperbolic geometry. In the course in hyperbolic geometry so far, there's been a minus sign here. And to compensate for that, we've been using round brackets for lines, along with capitals. Okay, so this is the Euclidean setting. It's slightly different. There's a plus sign there instead of a minus sign. Okay, what is the definition of the quadrants between 2 points? There's one point A1. There's one point A2. The quadrants between A1 and A2 is by definition the square of the difference between the x coordinates plus the square of the difference between the y coordinates. That's the quadrants between A1 and A2. And if we have two lines in the plane, and we want to measure how far apart they are, we're not going to use angle. We use the idea of a spread between two lines. So if there's the line L1, there's the line L2, then in terms of these three numbers and these three numbers, here's the definition of the spread between the two lines. It's 1 minus A1, A2 plus B1, B2, all squared, divided by A1 squared plus B1 squared times A2 squared plus B2 squared. And then it turns out, very pleasantly, by a equality that goes back to Fibonacci, or perhaps even to Diophantus, this in fact can be written more compactly in this form as A1B2 minus A2B1 all squared divided by A1 squared plus B1 squared times A2 squared plus B2 squared. So if you're just sort of joining us and you haven't seen this before, a very good exercise for you at this point is to make sure that you can understand why this thing is the same as this thing. So manipulate, rearrange to verify that. So that's a number that measures how far apart two lines are. And we make some definitions. We define perpendicularity of lines and parallelism of lines in terms of this spread. It's one way to approach it. So we can say that two lines L1 and L2, these ones here, are perpendicular precisely when the spread between them is 1. What does that mean? Well, if this is 1, it means that this has got to be 0. And that happens just when A1, A2 plus B1, B2 is 0. So that's when the two lines are perpendicular. Parallelism is defined in terms of the spread being 0. Well, when is this thing 0? It's easier to look here. This is 0 precisely when the numerator is 0, precisely when A1, B2 minus A2, B1 is 0, which is to say that the proportion A1, B1 is the same as the proportion A2 to B2. So quadrants between points, spread between lines, notions of perpendicularity and parallelism defined in terms of the spread. Those are the fundamental concepts for Euclidean geometry in the plane, the fundamental concepts to do trigonometry in the right way. And if trigonometry was taught with these as the fundamental concepts instead of distance and angle, well, life would be a lot easier for millions of mathematics students all around the world. So get on to your teachers, get on to your local educators, get them to know a little bit about this point of view and to start considering it. Make life a lot better for a lot of people. Okay, how does the trigonometry then develop from these definitions in the Euclidean affine case? Well, there are 5 main laws of rational trigonometry, and they're all on this page. And they concern 3 distinct points, A1, A2, A3. Now, if we have 3 distinct points, then there are associated to those points 3 quadrances and 3 spreads. And trigonometry is about the relationship between those 6 numbers. And here's our convention for the notation of those 3 quadrances and 3 spreads. So here's A1, A2, A3. And what this diagram is telling us is that the quadrants between A2 and A3, denoted by this little Q1 here with that little rectangle, that's Q1. Okay, so Q1 is the quadrants between A2 and A3. Q2 is the quadrants between A1 and A3. And Q3 is the quadrants between A1 and A2. That's our preferred notation for a triangle. And the 3 spreads, well, the 3 lines that are formed by these 3 points, they make 3 spreads. So this spread is the spread between this line and this line. In other words, the spread between the line A1, A2 and the line A1, A3. Call that S1. That's the spread S2, and that's the spread S3. And we put the spread here, but we could actually put it anywhere in 4 places because it's actually only the lines that matter when we are taking the spread, not rays. So the spread is a measurement between 2 lines. And this is just our one of 4 possible places to put that little notation. Okay, so what are the relationships between these 6 quantities? The first is Pythagoras' theorem, that if, say, A1, A3 is perpendicular to A2, A3, in other words, if this is a right angle, in other words, if this line and this line are perpendicular, and what that precisely means is that that spread is 1. So if that spread is 1, then Q1 plus Q2 equals Q3. And conversely, if Q1 plus Q2 equals Q3, then the spread is 1 and the lines are perpendicular. That's Pythagoras' theorem. That's actually more in keeping with the way Euclid thought about it originally. Q1 plus Q2 equals Q3. That's equivalent to this being a spread of 1. Next formula, the triple quad formula. It gives a condition for when the same 2 lines are parallel. When is this line parallel to this line? Well, they both go through this point. So in fact, that's just another way of saying that the 3 points are collinear. So this condition is exactly the same as saying the 3 points A1, A2, and A3 are collinear. They all lie on one line. And that happens precisely when this relationship between the 3 quadrants is satisfied. Q1 plus Q2 plus Q3 all squared equals 2 times Q1 squared plus Q2 squared plus Q3 squared. It's the second most important theorem in mathematics. That's the number 1. That's the number 2. Guaranteed. Spread law. The relationship between the spreads and the opposite quadrants is S1 divided by Q1 equals S2 divided by Q2 equals S3 divided by Q3. The cross law. The relationship between the 3 quadrants and one of the spreads. Well, we have 3 different possibilities for this cross law. This is the one involving S3. It says Q1 plus Q2 minus Q3 all squared equals 4 times Q1 times Q2 times 1 minus S3. So for example, it allows us to find the spread S3 if we know the 3 quadrants. Or if we know 2 of the quadrants and S3, then we have a quadratic equation for the 3rd quadrant. And finally, the triple spread formula, which gives a relationship between these 3 spreads, S1, S2, and S3. They're not just random. They have to satisfy this relation. S1 plus S2 plus S3 squared equals 2 times S1 squared plus S2 squared plus S3 squared plus 4 times S1, S2, S3. Okay, so those are the 5 most important formulas in geometry from my point of view. 1, 2, 3, 4, 5. The most powerful of these laws is certainly the cross law. It turns out in a rather interesting way that the cross law implies all of the other 4 laws. So in some sense, there's really only one trigonometric law. But it's a consequence of these 2. That's why these 2 get a sort of special preference. They're the fundamental bedrock of the subject. Okay, and as I show in my book, and as I show in my rational trigonometry series, with these 5 laws, you can solve all those engineering and surveying and geometry problems involving trigonometry much more elegantly, faster, more accurately, and with a lot more fun than with all that painful classical trigonometry with those sines and cosine and cosecant functions, which are all ultimately unnecessary for trigonometry. Okay, so that's rational trigonometry. Now we're going to turn to our main interest, which is hyperbolic geometry, and how does trigonometry look like in the hyperbolic setting. And we're going to see that the setup is very parallel to what I've just shown you here in rational trigonometry. There's a very close analogy between the definitions and the main theorems, but there are also important differences too. Let's have a look. Alright, so now let's turn to universal hyperbolic geometry. And in principle, You could start watching this series right now. I'm just going to tell you what the main definitions are without any motivation, without any pictures. Everything is purely algebraic. Everything is over the rational numbers. A point, what is it? It's a proportion of three rational numbers, x to y to z, in square brackets. That's our convention. It's usually given by a small letter, like a. A line. A line is a proportion of three rational numbers given in round brackets. We say that the point A is incident with the line L. This point is incident with that line precisely when L times x plus m times y minus n times z equals 0. That's our definition of when the point lies on the line or the line passes through the point. How we visualize points and lines is, in fact, a little bit irrelevant. The logic of the subject just resides with very simple algebraic realities. Here now is the definition of the quadrants between 2 points. So given 2 points, whatever they are, things like this, there's A1, there's A2, we want to define how far they are apart in some sense. Here's the right way of thinking about what that quantity is. It's the quadrants between 2 points. It's Q of A1, A2. It's given by this definition. Let's have a look. 1 minus x1 times x2 plus y1 times y2 minus z1 times z2, all squared in the numerator. In the denominator, 2 terms, x1 squared plus y1 squared minus z1 squared coming from there, and x2 squared plus y2 squared minus z2 squared coming from there. The first thing to note is that this is actually well defined. So if you multiply x1, y1, and z1 by some number, like 5, then this is multiplied by 5, this is multiplied by 5, this is multiplied by 5, so that whole thing inside there is multiplied by 5, and when we square it, we get a factor of 25 coming out. Down here, this is multiplied by 5 squared, by 5 squared, by 5 squared, so there's a factor of 25 coming out of here. This is unchanged. So the 25s cancel, and that means that when we multiply this by a scalar, the quadrants doesn't change. So it really is a well-defined quantity. The spread between 2 lines. Well, points and lines are kind of obviously dual. They look exactly the same, except that we've got square brackets and round brackets. We're going to just repeat the definition of the quadrants for the spread between 2 lines. It's exactly the same. So the spread between this line L1 and this line L2, it's 1 minus L1, L2 plus M1, M2 minus N1, N2, all squared, divided by L1 squared plus M1 squared minus N1 squared times L2 squared plus M2 squared minus N2 squared. So you can see now one reason why I showed you the definition of the quadrants and spread in the rational trigonometry case, because these both look a lot like the definition of the spread between 2 lines in the Euclidean case. There was also 1 minus something, and it kind of looked like this. In fact, it looked a lot like this. If there weren't any z's, you'd see that it was exactly the same as the previous definition. Now, one more thing that we do with these things, with the Euclidean case, we use the notion of spread to define perpendicularity and parallelism. We're going to do half of that here. We're going to say that 2 lines are perpendicular precisely when the spread between them is 1. So this spread is 1. In other words, if this quantity here, the second part, is 0, in other words, when this quantity L1, L2 plus M1, M2 minus N1, 2 equals 0, then the 2 lines are perpendicular. It's another way of saying what perpendicularity means. And once we've done that, then duality almost obliges us to say the same thing for points. So we define points A1 and A2 to be perpendicular precisely when the quadrants between them is equal to 1. So these 2 points are perpendicular precisely when q1, q2 plus y1, y2 minus z1, z2 is 0. So we're always going to keep the symmetry between points and lines and between quadrants and spread. It's a main feature of the trigonometry in this universal hyperbolic setting. So those are the main definitions. Now what are the main laws? What do the laws of trigonometry look like in this hyperbolic setting with these definitions? So here are the main laws. There are 4 of them. Not 5 as in the previous case, there's 4 of them. But in some sense you have to multiply the 4 by 2 because there's kind of dual formulas for each of these. But let's just stick with the first 4. So our notation is we start with 3 distinct points, A1, A2, and A3. And our notation for quadrants and spreads follows the same pattern as in the Euclidean case. So here's a kind of a picture. There's say A1, A2, and A3. Then we'll agree that the quadrants Q1, little q1, is the quadrants between A2, A3. The quadrants Q2 is between A1 and A3. And the quadrants Q3 is between A1 and A2. The spread S1 is the spread between the 2 lines of the triangle emanating from A1. So the spread between this line and this line. And we can put that spread S1 wherever I want to. It's a little bit crowded in here, so I decided to put it here. Okay? But it still denotes the spread between this line and this line. That's spread at the vertex A1. There's the spread S2 at A2 and the spread S3 at A3. So we have 6 numbers and we're interested in the relationship or relationships between those 6 numbers. And the first, most fundamental theorem, as always, is Pythagoras' theorem. And that concerns what happens when 2 of the lines are perpendicular. So suppose that A1, A3 is perpendicular to A2, A3. So that line and that line are perpendicular. I remind you from the previous slide what that means is that S3, this number, is equal to 1. In that case, the theorem says, in that case, Q3, this quadrants here, equals Q1 plus Q2 minus Q1 times Q2. It's almost the same as the Euclidean Pythagoras, except there's an additional minus Q1, Q2, a quadratic kind of deformation. Note also that the implication is not both ways. This implies this. I'm not saying this implies this. Next, the triple quad formula. The 3 points A1, A2, and A3 are collinear implies this relationship between the 3 quadrants. Q1 plus Q2 plus Q3 squared equals 2 times Q1 squared plus Q2 squared plus Q3 squared plus 4Q1, Q2, Q3. And I hope that looks familiar. That's exactly the same form as the triple spread formula in rational trigonometry. The 3 spreads of a triangle in rational trigonometry have the same relation as do the 3 quadrants of 3 collinear points in the hyperbolic setting. But we still call this the triple quad formula because it's really concerned with quadrants. The spread law is exactly the same as in the other case. S1 over Q1 equals S2 over Q2 equals S3 over Q3. The cross law is more complicated. So have a look at it. It turns out to be a beautiful formula, and we'll grow to love this formula, I hope. But let's have a look at it now. It looks a bit intimidating. It's a formula involving 3 quadrants and 1 spread. Q1, Q2, S3 minus Q1 minus Q2 minus Q3 plus 2. You square all of that. What you get is 4 times 1 minus Q1 times 1 minus Q2 times 1 minus Q3. So if you knew the 3 quadrants and you wanted one of the spreads, you could get a quadratic equation for the spread. Not quite as good as in the Euclidean rational trigonometry case where you get an actual formula for the spread. Here you got a quadratic equation for it. Okay, so in my opinion, these four formulas, next to the 5 formulas I showed you for rational trigonometry, are the most important formulas in geometry. So altogether, I've shown you 9 of the 10 most important formulas in geometry, in my opinion. So the 5 for rational trigonometry and these 4 are just absolutely fundamental formulas, not just for hyperbolic geometry, but it will turn out for spherical geometry, it's exactly the same formulas, or elliptic geometry, perhaps better to say. In fact, for any quadratic form, eventually we'll talk about that, so these are universal formulas, they still apply. And we're going to see many beautiful applications of these formulas, and you will grow to appreciate them. They're lovely, and they're powerful, and they allow us to do trigonometry much, much more efficiently than the trigonometry involving sines and coshes and tangents that you find in all the textbooks. So it's very literally true that these formulas basically consign all those previous textbooks to the dustbin of history. They're like dinosaurs in terms of the power of the technology. We'll see this. You'll see exactly what I'm talking about. Okay? These are very beautiful formulas. You will learn them really well in this course. And now let's have a few exercises to get us used to thinking about these quantities and these relations. So a lot of these exercises are algebraic. This gives you a chance to practice your algebraic manipulation skills and to become familiar with the formulas, move variables around, take things from one side to another, play around. Okay, so the first one, this crucial quantity that defines the quadrants or the spread, show that this 1 minus this term here can be rewritten in this form. So notice there's a minus sign here, very important minus sign. And then it's something that looks a lot like the alternate formula for the spread in Euclidean case, where there was only sort of one numerator term, essentially this one here. So there's 3 terms here, 2 of them with a plus sign, 1 with a minus sign. Show that the Pythagoras' formula relation, Q3 equals Q1 plus Q2 minus Q1, Q2, is equivalent to this formulation. 1 minus Q3 equals 1 minus Q1 times 1 minus Q2. Show that the cross law implies Pythagoras' theorem. Show that the cross law implies the triple quad formula. And show that the cross law implies the spread law. Giving you an idea that the cross law, just as in the Euclidean case, is the most powerful law, even though it's seemingly the most unwieldy. It kind of contains the most information. And now let's do a little bit of computation to verify some of the laws. So in this exercise, I ask you to compute the quadrants and spreads for our first standard triangle. I remind you that's the triangle which has these 3 as its points. Second exercise here, find a right triangle, in other words, one with 2 lines perpendicular. Find any one, and verify Pythagoras' theorem. Compute 3 quadrants, check that they satisfy the Pythagoras' theorem. 21.8, write down the dual laws and verify them in some cases. So each of these laws has a dual law that you get by simply interchanging the quadrants and spreads and the points and lines. So I want you to go through those 4 laws and make sure you think about what the dual laws state, what they're telling us, and verify them in some cases. And here you can verify the spread law and cross laws for that first standard triangle whose quadrants and spreads you computed up here. All right, so this has obviously been a very important lecture. We've introduced the main notions. We've introduced the fundamental laws. I've shown you 9 of the 10 most important formulas in all of geometry. Okay, so it's pretty important. If you're learning hyperbolic geometry some other way, all right, you really should be exposed to this. So if you know someone who's learning geometry or hyperbolic geometry another way, do them a favor and send them an email with a link to this video. Okay, this video is Very important to reorient your thinking about what's important metrically when we're studying hyperbolic geometry. Okay, so we have our work cut out for us now. We want to understand these laws. We want to prove them. We want to see how they work in practice. We want to get some feel for them. And the best place to start is with the first one. So next time we're going to look at Pythagoras' theorem in the universal hyperbolic setting. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.